Okay, so now we are going to consider how to predict y using x. Actually, it's pretty simple. The idea is pretty simple, because think about the example of marginal cost and fixed cost. We estimated the marginal cost and the fixed cost. Then prediction of the total cost is pretty much automatic. If you choose how much you are going to produce, then you can use the fixed cost and marginal cost, and exactly that's the microeconomics example, right? And in regression analysis, so this is how given that you decided to produce, say, 10 units or whatever, certain number of units is the output production, then your estimated predicted total cost it's like following this form: estimated fixed cost plus estimated marginal cost times the production amount, right? Just use the estimators. And of course, the epsilon, the error term, cannot be predicted. And of course, you just ignore the error. If there is no error, this is the predicted cost. And in regression analysis, we call y hat the predicted value of y given x as the fitted value. So we call this fitted value. So that's the predicted value of y. And in our example again, the fixed cost is estimated to be around, say, look at this. So this is the estimated fixed cost. This is the estimated marginal cost. Then use that. So I'm going to round them up like one step further, so like this. Then, so use the fixed cost and the marginal cost and apply that. If you produce 6.5 units, then your total cost would be 23.67. So you predict y even if you have never produced 6.5. In your data, you have produced 6, sometimes 6 or 7 or 1, 2, 3, 4, but you have never exactly produced 6.5. So what you are doing is you are kind of interpolating those observations and predict what would happen at 6.5. Okay, so that means like on the scatter plot, we draw a trend line. That's the regression line. Regression gives you a trend line, and then you choose how much you produce. This is the production amount, 6.5. Then just go directly up and find the function value, the value of this regression equation at this point. This is, if you go to the left, it's like 23 point something. So that's how you use the regression for prediction. So pretty simple if you look at this example. Okay? So then, now I will ask you to do this. Do the same thing. Using the same predicted, like estimated fixed cost and marginal cost, predict the total cost when you produce 5 units. Must be pretty simple. Okay, so calculate that. Fixed cost is 8.2 plus 2.38 the marginal cost times 5 units. So you can do the math. Then you will get $20.1 is the total cost. This is the fitted value for X. But think about this. In our data, we did observe 5. Output of 5 was in our data. So let's compare this. So this was our data. So we've produced 5 units here and here. So, and our actual cost was 21 and 22. But we could recalculate the predicted cost 20.1 for them, right? So there are difference between the actual observation and what you predict. Your prediction can be different from your actual cost. you may understand the difference as an error term or an like estimation error. So and also similarly, by following the same steps, you can assume output equals 2 and predict the cost again and compare the predicted cost at this observation with the actual observation of the cost. So actual cost and the predicted cost are different for almost every observation. Yeah, strictly every observation has difference between the actual cost and the predicted cost. Graphically, so that is called residual. The fitted value, the predicted value, and the actual realization are different. That can be denoted this way. Y is the actual observation, and Y hat is the predicted value. Their difference is denoted as epsilon hat. That is called residual. And graphically, you can imagine the regression line going through the observations, but not exactly connecting the dots, right? So there are differences, deviation from the line, predicted line. So that deviation is the residual, right? Residual is residual. This is so the difference is like when you produce 6 units, you actually spent this much from the past, but you can predict it to be this much. So the difference is some kind of error, estimation error, like accounting error, production error. I don't know where the error is coming from, but it is an error, residual. So then again, so remember, it is another kind of transformation because for each observation, you calculate the predicted value. So then you have as many predicted fitted values as many as the sample size. And also you can calculate the residual for each value, for each observation. So there are as many residuals as the sample size. So it's like exactly transformation of a random variable. X is a random variable you observe. Y is another random variable you observe. By some transformation of them, you obtain another random variable which is called the fitted value. And then by taking difference between these two, you transform and obtain another random variable called the residual. So imagine it as theoretically, it is just a kind of transformation of a random variable. So you have as many observations as the sample size. Okay, now we are going to look at the residual. The predicted value is easy to calculate, easy to interpret, and so I think that's pretty much it. But we have, like, there are some interesting results based on the residuals. So put it this way. The residuals can be interpreted this way. The actual outcome, so remember, this is the fitted value. You are going to predict Y this much. So then the difference between the actual outcome and the explained predicted outcome, difference between them is the residual. So your observation can be decomposed into your predicted part, predictable part, plus unpredictable part. So explained part and unexplained part. So explained by the regression model, but this is residual is unexplained. That is not explainable by your regression model. So this is simple decomposition, right? And then, of course, in your regression, you want this part to be small, obviously. You want to minimize the unexplained part. You want to explain as much as possible, and you want to predict almost everything, every part of the outcome. So that's a natural way to interpret the residual. So you want small residuals, which means on the scatter plot, all the observations are closer to the line, which means the relationship is stronger, right? And also your prediction will be more accurate. So your prediction will be accurate. So this is, you can think it as a measure of the accuracy or how good your model is. We are going to use this idea to evaluate the regression model. So think about this. Compare 3 examples. This is an ideal example, but where there is no residuals. All the observations aligned in a perfect trend line, but it's impossible in practice. We don't see this data at all. We cannot see. So in this case, this is perfect relationship, linear relationship, but impossible in practice in real data. So then you may see these kind of things. So of course, the first one, the left side graph, is stronger relationship than this one. There are more residuals, right? We see this in the previous chapter. This graph implies correlation, stronger correlation coefficient. And this is correlation coefficient closer to 0. And this is closer to +1 because the direction is positive, right? So residual, small residual implies correlation coefficient close to +1 or -1. Stronger linear relationship. So they are interconnected. And residual also can be interpreted as the goodness of the prediction, how good the prediction is. So we will use this idea to derive the estimator. What is the best? So we would like to minimize the residuals, and the estimators that minimize the residual is our estimator. That's what Excel calculates. And second, then we will evaluate the accuracy of your regression model using the residuals, right? So based on the residuals, we can do these 2 things. First, let's think about this. So, like as I promised, so far we considered the Excel results as given, but I did not explain how they are calculated. Now I'm going to calculate. So it is so as I said, it's to estimate the intercept and the slope, or drawing a line on the scatter plot. Then our question is how to draw the best line. What is the best fitting trend line on the scatter plot? To do that, we are going to consider the residual first. Remember, the residual was calculated as the difference between the actual observation minus actual y minus predicted y. And prediction was calculated by this. So that means if you change your estimator, intercept and slope, your residual will change. So what you want to then, idea is you want to minimize this. You want to make the residual as close to 0 as possible by choosing beta 0 and beta 1 deliberately. That's what you're going to do. So then, how can we do that? Close to 0. Close to 0, not just small. Close to 0. So if epsilon is negative, it should be close to 0, which is greater. And if it's positive, close to 0. So minimization problem can be written in this way. I will take square of the residual. Then this means if the residual is moving away from 0, either direction, the square will increase, right? A square function is like so square function looks like this. So minimized at 0, and it increases as you go outside, right? Drastically, like quickly become larger to the positive side when epsilon is different from 0. So and the residual, there are as many residuals as the sample size. So you are going to square each of them and sum them over the sample whole observations. So we are going to use this as the total size of the residuals. So there is a specific name for this. This is called the residual sum of squares or sum of squared errors. I really hate the names. Different textbooks use different names, but I will follow Excel. Here, this is residual sum of squares. Let me rewrite this. This means sum of squares. So residual sum of squares is 29.46. So that's the residual sum of squares in our estimator. So, but as I said, it may be different. This residual sum of squares may change when you change beta 0 and beta 1, right? So we are going to minimize it. Minimize sum of squares inside the parentheses is the residual. But residual is calculated by beta 0 and beta 1. So you have to choose those two parameters deliberately to minimize this guy. So we call this the least squares. You know what it means. It's now straightforward why it's called least squares. We find the estimator that gives you the least sum of squares of the residuals. So we call that ordinary least squares. So because later there are different least square methods are proposed. So we call them generalized least squares. So as opposed to them, it's kind of the original ordinary least squares. So OLS is often the name for this. Anyhow, you get it? So these numbers are calculated to minimize this residual. So in our results, the residual sum of squares is 29, but if you change it, those numbers, it will increase. You will have more residuals, right? That's the idea. So as I said, So these coefficients are deliberately chosen to minimize this number. Right, for example, this is an example. So the red line is, I think the green line is the estimator. What Excel suggests you. Excel suggests you to use this trend line, green. But let's see, you want to draw the trend line like the red. So choose a different number. Say, I think the fixed cost is 5 and the marginal cost is 3. Then if you recalculate the residuals and calculate their sum of squares, you get 56. Much larger residuals than the OLS. OLS will be so if you change the number, always the sum of squares will change. So the minimum is what you have in Excel. Okay, I will stop here, and in the next video, I will give you the relationship between those OLS estimator with the correlation or covariance coefficients. Okay, thank you for watching. See you later. Bye.